science is not immune from sort of like the mob mentality of like, oh my God, like this thing is shiny. Let's all go in, and periodically things get kind of accepted as some form of the truth, right? And people keep kind of like regurgitating them until that right until that so-called truth runs into enough tension with the new data that at some was, it usually requires somebody, typically, a graduate student, to come in and say, like, uh, I think it's the opposite of what you guys have been saying. And then it goes through the usual cycle, which is, again, has parallels. It goes like when new ideas that are very interesting that are put out. First, people say it's wrong. Then people say it's irrelevant. And then they're like, well, actually, I came up with that first.
Oftentimes you talk to scientists and they have this attitude of, we know everything and the lines are drawn and we're done figuring it out. But I think that Professor Batygin has this understanding that things will change, and as you push the boundaries, there will be shifts in understanding.
And they don't change necessarily by jumping up on the megaphone and being like, this is all garbage. They change through this really careful process of collaboration, refinements, mathematicians working together with really heady theorists, people who are interpreting the data, working together with experimentalists who are able to make sense of the mechanics of what's happening. And I really appreciate that.
Yeah, we cover quantum physics, we cover cosmology, we cover solar system formation, star death. We run the entire gamut, and it was a great conversation. You're going to really enjoy it.
If you're already supporting us right now on Patreon, we love you. Thank you so much. If not, and you can spare a few dollars to help us keep the lights on, maybe help crank up the quality of this show, get more episodes out, we really, really could use your support. If you don't have any cash, that's fine. Just share the episode with somebody you think would enjoy it. Share it with your friends, share it with your family, and hopefully we'll be reaching more people soon.
And for now, enjoy the conversation with Professor Batygin.
The scientific revolution starts now.
Deep is the first podcast.
Let us see in the dark.
Did you ever make a decision between music and astronomy, or?
I sort of didn't have to, right? Because I keep the band going, right? We're always writing new stuff. The good news is I don't have to depend, financially on doing music, right? Which is freeing in a way. I really don't worry about what anybody else has to say about the songs that we do with the band. So we kind of do it for fun, but also we do it seriously, right? We don't just kind of screw around and have it not go anywhere, right? We put real effort and time into it. And so in a way, I kind of feel like I get to enjoy the best of both worlds, right? It's easier to also do music on the side while being a professor of astrophysics. It's harder to be a full-time musician.
Yeah, I was gonna say it's almost impossible for people, right? It's like, who can actually pull that off these days? I have so many friends who are trying to be professional musicians, and it's just harder. It's harder than ever, It's not 50 years ago when there's these $20 discs you can sell everybody and all of that, or whatever, the LPs, and there's no products really. It's a strange moment.
Absolutely. And moreover, it's further strange because for a long time the lore was like, oh, as the CD died, right, the profits of the music industry, right, completely plummeted, and therefore it's hard to be a full-time musician. But if you look at kind of like the revenues of the music industry right now, they're kind of back to where they were in the 90s. So it's largely recovered without musicians getting a take, so to speak. So it is indeed a very strange moment in time, and we'll see. I think it's pretty unpredictable where it's going to go.
We're Oh, go ahead.
Good.
I was going to say we're definitely living through an era of deep bureaucracy because I think that the structure where the organizers and the people that are writing the notes and running the house, so to speak, are the ones that are getting the big take, and the people that are actually doing the work are not necessarily
There's
getting the sort
something
of
different
preference.
about the past, the way the music industry was structured too, where record labels would take a risk on bands. They would record way more records than they would ever get a hit out of, right? So there's all these one record wonder bands, right? They have these very elaborate productions, like huge string sections, horn sections, just unbelievable gobs of money and time put into them, and they have like one record. And it's like, well, if you're a huge record label and you've got Jimi Hendrix or something that's basically paying for all these other bands. And I don't know that the label structure or the bureaucracy is set up in the same way as it used to be to afford these kind of adventures. I have no idea. It just seems like a very different world. Yeah.
Yeah, I think it used to be set up a lot more like a VC fund, if you will, right? Where you kind of take a chance on 100, artists. One will become huge, right? And kind of pay for the other 100. It's unclear to me that these days, like the album has any meaning at all, right? I can't. I mean, there are a few bands that I'm like kind of a huge fan of, where like when their album comes out, I will sit down and fully, listen to it multiple times. And for much of the rest of the music, it's a lot like clothes or something. You put on clothes in the morning, you take them off in the evening. Like it's just like kind of comes and goes. So I think that kind of rapid turnaround, right, kind of diminishing.
It's like it's more of a commodity now or something, right? Like music's just so come and go. There's music everywhere pumping out of every single speaker, and I'm not sure it was always quite that way and also like the decentralization of the equipment is really interesting today too, right? Because I feel like 50 years ago, a few companies would have access to this like multi-million dollar equivalent studios and this whole technological pipeline to crank out these records. And nowadays, yeah, we can all basically make records at home, but there's not that same central distribution point either. So
Right, right. I think it's, in fact, yeah, go ahead. That's it.
Oh, what I was going to say is that it seems like you would expect that to expand the horizons of what people are doing and the strangeness of the music, and you would expect it to really bring a cultural renaissance. But I feel like there is this sense of culture being stuck, of people making very similar things that they've always been making, and everybody's very conservative, and the studios are very conservative. We have friends, there was what's the studio that does the modern Motown records?
which one? In
Oh, Lee
Brooklyn?
Fields, yeah, the one that's in Brooklyn. Like Lee
I
Fields and the
forget.
Expressions. It's basically Motown, and it's beautiful. It's wonderfully produced. They're beautiful songs, expertly performed. They're amazing, but they're Motown. It's not Motown with a twist. It's just it's just a recreation of what was once popular and beloved, which is really interesting to me.
Batman 57.
Yeah,
That kind
yeah.
of thing.
That's an interesting point. And more generally, to kind of agree with you on this topic, I think there are certain products, if you will, that we consume where perfect competition is a good thing, and probably music is not that, right? I mean, if you think about like lettuce, right? Like I don't go into the store and think about a brand of lettuce that I'm going to buy. It all looks the same to me, right? And so every brand is in this perfect competition of all lettuce. It costs the same exact amount, and we're just like consume whatever. You can't really apply that same thinking to music, but I think at the same time, that's the kind of economic model, is that we're just putting out a bunch of stuff, right? It's all kind of equivalent, right? Motown is Motown. It's going to sound like Motown. You know what to expect. And, on the consumer end, I think you're right. There's a bit of loss of originality. At the same time, I've actually been recently become more optimistic, I guess, of the state of rock, because I feel like rock has kind of bottomed out, in its popularity, um, and it's almost always that when that bottoming out happens in a given genre, that new things get created, because there's absolutely no reason to play rock music, right? Other than that, if you really, really want to, right? And so it's that moment of really, really wanting to that leads to kind of new branches. So I'm optimistic about the future. Maybe not the present, but I'm optimistic about the future of rock music.
I like
Do you
that.
see like a similar parallel in science also?
Exactly what was
Oh,
I was
yeah.
gonna ask.
Yeah, where just,
Oh,
people keep making the same Batman movie over and over until something actually like the floor falls out from underneath
mhm.
things.
Absolutely. And in fact, science is not immune from sort of like the mob mentality of like, oh my God, like this thing is shiny. Let's all go in. And periodically things get kind of accepted as some form of the truth, right? And people keep kind of like regurgitating them until that right, until that so-called truth runs into enough tension with the new data that at some was, it usually requires somebody, typically, a graduate student, to come in and say, like, uh, uh, I think it's the opposite of what you guys have been saying. And then it goes through the usual cycle, which is, again, has parallels. It goes like when new ideas that are very interesting that are put out. First, people say it's wrong. Then people say it's irrelevant. And then they're like, well, actually, I came up with that first.
We already
Right.
knew that.
So,
Yeah. I think it was
yeah.
William James who said that first. Can you think of an example of this happening like in your own career where you've seen
Oh,
some paradigm take a hard right turn or something like that?
well, I mean, there are many of them, but one interesting example that comes to mind actually is sort of like the story of how extrasolar planets, the story of the first kind of exoplanets that were discovered and their origins. So the kind of first class of exoplanets that were found in large numbers were these objects called hot Jupiters, giant Jupiter-like planets. But what's weird about them is they orbit their stars on sort of in a matter of days. Okay? So when they were discovered, the kind of immediate paradigm for how they formed became, well, they all form just like Jupiter, and then they all migrate through the disk, through the natal protoplanetary disk, until they stop at the inner edge, and that's how it works. Okay, and everyone sort of agreed that that must be the answer, right? And when people agreed that must be the answer, it sort of became the lore. Um, in parallel, right? It again, I don't remember who was the first to point this out, but I think but it was sort of a few kind of people come to mind, like the papers by Fabrici and Tremaine, when Fabrici was a grad student, right? Pointed out that there's a completely different way of making these giant planets, which is that you start them out where Jupiter is, but then you perturb them onto a high eccentricity, very elliptical orbit, and then they kind of get tidally captured onto a tight orbit around the star. So then the community largely shifted towards that being kind of the standard mode of the truth. And this is all like in the span of 20 years, right? So these are I don't want to call them fads. These are just kind of, you know, directions of what people believe to be true. And we've, like, my collaborators and I have also thought about this problem a bit, and we're like, wait, all of this, all of these stories start out with the giant planet being somewhere far away and then like migrating all the way down. But like, what's the evidence for that? What is the evidence for everything needing to form, where Jupiter is, right? Is that not simply our, biased by our own solar system? And to an extent, right, the two things cannot be divorced, right? Our solar system is also a product of the planet formation process. So you can't say our solar system is somehow special and all of these things are distinct. But nevertheless, we kind of looked into whether or not you can just form these things where they are? And the answer is you can, right? So maybe sometimes the simplest explanation of, can you just accumulate enough solids, right, to make a core of a giant planet, and then will it go through its core nucleated instability and grow a large envelope? The answer is that turns out to be yes. So, in just a short span of 25 years, we've kind of gone through a bunch of iterations of what we think is the common outcome.
And it's interesting because I feel like those aren't all mutually exclusive. Like you could have different planet formation mechanisms in different places under different conditions. Like we had Gabor Bajri on the show a few months ago talking about brown dwarfs and really just like how similar they are to gas giants in fact. And then, you couple that to planets migrating orbits, and it's like, maybe there's something to that as well.
It seems like the last century of science has really wanted to be able to have a single story to tell, where this is the story in capital letters. And when you look out at nature, it seems incomprehensible that for the vast diversity of objects, that you would have a single linear path towards their formation.
I think you bring up a really important point, which is that I think in kind of fundamental physics, right, that reductionist point of view has been really successful, right? You reduce things down to the very, very kind of core principle, and then from it, everything flows. So I think, that's absolutely been a success. On the other hand, as we go as we go higher up in the levels of complexity, away from just fundamental physics, to kind of examine what the world actually looks like, right, that reductionist point of view begins to fail. Because after all, right, a insect is way more complicated than a star, right? Like a star, we can still understand from first principles, right? There's hydrostatic equilibrium, nuclear fusion, and it's basically a ball of ideal gas. And yes, there's like corrections, there's magnetic fields, but if we ignore kind of the corrections to leading order, we can understand it. But we can't understand an insect from from first principles point of view. You're not going to be like, well, okay, let me write down the wave function for an ant and solve the Schrodinger's equation for an ant. Right? That just makes no sense. And so planets,
And honestly, like the Schrodinger equation starts to, like, that gets even overly simple when you even talk about like water molecules or something like as simple as a couple atoms combined, right? It's like, oh, just forget about your simple wave equation. It's like you got like hybridized orbitals, and like I think water has something like 50 different energy state. Like it's all over the place. It's not just this nice P and S orbital business that you learn about.
Yeah, it's actually I've been sort of obsessing over this topic. There's not a well understood connection between how you graduate from quantum mechanics to the classical world, specifically for chaotic systems. So like for systems that are well localized, that behave where the number of quantum numbers is equal to the number of degrees of freedom, which is the case in the hydrogen atom, right? It has 3 quantum numbers and 3 degrees of freedom. Right, you can actually solve that perfectly well. For a helium atom, it's no longer true, and generally, right, and helium is not not a very sophisticated atom.
And this just means that it's vibrating in lots of it's the vibrations become less predictable. They're less stable or something like that. If we think about like spherical harmonics as the ideal atom shape or something like that.
Well, so you can't associate a given energy level for a helium atom, for example, with a specific spherical harmonic, right? You have to do perturbation theory and write it down as a series. But more generally, right, the fact, what if the system that you're considering is chaotic, right? Then you really have a bit of a problem.
What do you mean by chaotic? I'm sorry, real quick. Like, what do you mean? Like there's multiple atoms like crashing into each other? Is that what you mean, or?
Well, let's go simpler, right? Like imagine the classical world and put a pendulum on top of another pendulum, make a double pendulum. That system is unpredictable, right? It's in fact, when I was an undergrad, there was a model of there was like a a physical double pendulum in the like kind of undergraduate lounge at UC Santa Cruz. And I used to sort of like, when I would walk by, I'd play with it, and I'd be like, man, this thing is like swinging left and right. And I had no idea about the fact that it was unpredictable. It was, I think, in my third or fourth year that I read the little plaque next to it that said the reason you can't predict what it's going to do is because it's unpredictable. But now imagine taking that classical system and quantizing it, right? You write down Hamiltonian, do the usual thing, replace the P by an operator, right? And you solve the Schrodinger equation. But the Schrodinger equation is linear in a wave function, which means that it cannot possibly yield truly unpredictable results, right? The fact that the equation is linear kind of limits the amount of unpredictability it can have down to zero. And this is like a well-known thing, there's quantum suppression of classical chaos. So how you graduate from a quantum chaotic system to a classical chaotic system remains an area of research, and there's no single answer to that.
It seems like in general, like the translation between the quantum level, this highly abstract mathematics to a material basis upon which you get chemistry and all of these other very physical interactions is a ripe area for research right now.
Oh yeah, the correspondence principle between the classic and quantum world is far more interesting than kind of what the typical introduction to quantum mechanics book will tell you. The book will just tell you, you take h bar to zero and you will, your wave packet collapses to a point and that becomes a classical trajectory. But it's actually more subtle than that. And that subtlety, that subtlety begins to really manifest in specifically chaotic systems, right? In systems that are unpredictable, you will have weird things where a classic variant, an isolated classic variant of the system will kind of diffuse for a while, but then its diffusion will get limited by really the fact that it runs into h bar as the fundamental scale over which mixing can take place. So the way to understand, or at least the way I understand it, is this: in the classical world, classical mechanics, right? Everything obeys the Liouville equation, which is a statement merely of the fact that a bundle of trajectories, right, will conserve their phase space area. So it's kind of like if you put down red paint onto a table and drop some white paint on top of it, and then start mixing, right? Which is what chaotic systems do. That white paint, which represents some bundle of trajectories, can get mixed up into red paint to arbitrarily fine, to an arbitrarily fine degree of filaments. But in the quantum world, once you do that mixing and the filaments of paint get smaller than h bar, it makes no sense to then go finer than that. So then the quantum world kind of tells you that's enough mixing, right? That's as far as you can go. So there's a real discrepancy there. And you would think that this is some like weird thing that will manifest on something like 100 million times the lifetime of the universe, and like this is not something you could ever observe. But for simple systems, like the time scale for this to manifest can be a few like characteristic Laplace of times, right? If you imagine a quantum version of Hyperion, which is a satellite of Saturn, which rotates in a chaotic manner, right? Chaos spins unpredictably, and you replace that with a quantum Hyperion, right, and solve that problem using the Schrodinger equation, what you will find is that chaotic rotation will become suppressed on a timescale of something like 22 years, right? So it's like a weirdly human timescale. Of course, no one believes that Hyperion will really start to not spin.
Or will it just become predictable at that point? What does it mean to be suppressed to zero?
Yeah, it sort of goes into a quasi-periodic state. It finds a quasi-periodic state. In the quantum world, in the classic world, it doesn't.
I mean, it sounds to me just like the tool, the mathematics that's being used there is just inadequate in that situation to describe what's happening or something like that. It's like sort of the limit of the ability of that drill. Like it just can't tackle the material that you're trying to drill through or something like that.
Maybe, but it's also it seems like it could be related to something physical where if you have a limit at which things mix and you have a limit at which they can interact, it's almost as if you've reached some fundamental.
Yes, but at the same time, we see that get violated all the time, right? Like our classical world is not periodic. Our classical world very much has random things happening. And in fact, that's all of the transport, even at a relatively microscopic scale that we see, is due to chaos in the classical world. So, because if it wasn't, then everything would kind of be a repetition, right? You'd be able to write everything down as some linear set of, eigenmodes that eventually will repeat, and our world would never kind of evolve, right? Like the entropy would be limited in its growth. So we see that violation all the time, and I think the conventional answer to how this gets accomplished in the literature has to do with the collapse of the wave function, right? People say, well, it's actually what happens is the wave function collapses all the time, so you never get to that 22-year whatever time scale you need to see for chaos to get suppressed. You kind of reset the clock all the time. But I think that's really where it's not so much even the mathematical methods they're becoming confusing. It's sort of the interpretation of quantum mechanics that reaches the question of like, how does the collapse of the wave function actually happen? Like I don't know. I'm actually, it's weird. I find myself in a situation where it's weird. I'm talking about this like I'm not an expert at all in anything.
No worries, neither are we. Yeah, it's just curious.
But it's a good question, right?
I mean, it makes me think a little bit of boundary conditions. My background, my PhD is squarely in material science, and so whenever we're trying to characterize some material property, particularly like harmonics, elastic harmonics. I worked a lot in elastic harmonics. It's very important to bound your statements, right? Your mathematical statements. And like if we were going to characterize the orbits of the planets, like we could do that with a very simple mathematical statement, but it wouldn't work sometimes, right? So we'd have to find a way to put the boundaries on that statement properly. And I wonder if there's something at play with regard to boundary conditions as we get down into the smaller and smaller level where there's just events that we're not sure how to characterize that interfere with our ability to make more generalizable statements.
It's a good question. Yeah. I wish I had a unbounded answer, but all I have is a bounded one, which is like, I have no idea.
Do you think that the quantum processes are involved in the assembly of planets and solar systems, or is it such a negligible effect that it doesn't?
Yeah, so it plays a role, which is a remarkable role. So so much of the outcome of planet formation ends up kind of depending on the chemistry of the disk. Right, planet formation starts out with first the star, like big ball of hydrogen helium gas collapsing, right? It makes the star, and because of conservation of angular momentum, some of that material has to go into orbit. You make this disk of hydrogen helium, plus a bunch of other stuff sprinkled in through the disk, and that's where quantum mechanics begins to really play a role, because the opacity structure of the disk is ultimately controlled by quantum processes, and the consequences of opacity structure of the disk and more generally the kind of chemistry of the disk dictates what you're going to build in it. So at the fundamental level, quantum processes are really important, and quantum mechanics is really unforgiving in a way, right? If you're asked like how many drops of dye do you need to dye a pole red? It's like 3 drops, right? It's amazingly like it's amazingly effective at altering opacity. So all I guess I'm trying to say is that we really do see at the end of the day the consequences of the quantum world because we're standing on one. Right? Well, I'm sitting currently. My office chair. I'm sitting on one. Yeah.
Can I ask you about that disk collapse process a little bit more? Because we've talked to a few different people, and I always try to hear different astrophysicists' take on this process because it seems like it's explained very quickly in most textbooks, especially intro astronomy type textbooks. And you mentioned chemistry, and I know there's a lot of stuff going on there. It's not because people often have a hard time imagining how in the vacuum of space, if you release a bunch of gas, you pop a balloon or something, how does that turn into even if it's a huge balloon, how does that turn into a star? How is there enough attractive processes going on?
And how do you get enough metal to form the center of a rocky planet, right?
Let's hold off on that though. I'm just trying to understand the stars for a second. Yeah.
Yeah. Okay. So let's go with that analogy of you got your balloon, right? You pop your balloon in space, right? Of course, suddenly you kind of release the boundary of the thing that's holding the gas together, right? The atoms have some velocity, so they have some temperature, right? They have pressure, and so now they're free, and so they all blow apart. Okay, right? And at the same time, right? Well, a balloon, a conventional balloon is a bad example because there's enough energy for them to escape the gravitational pull of the balloon. But imagine you have a very, very large, solar mass balloon, and it's also and the temperature is like 10 degrees, right? So the atoms are moving really, really slowly, right? And you pop the balloon, and sure, they blow apart. But as they blow apart, they see the overall gravitational pull still of the collective gas. So as they go, they slow down, right? Then eventually they reach some equilibrium where now the gas is kind of dispersed, and it's sort of in this balance between the kinetic energy of the gas, right, being kind of balancing the overall potential energy. And in fact, to be in equilibrium, the kinetic energy has to be 1/2 out of the overall potential energy. And then you have this ball. Okay. Does that make sense so far?
Yeah, I think so. I'm just trying to imagine like the scales. I think what it comes down to for me is just imagining a place that's so dense already, like a gaseous region that is so dense. It's very difficult to.
It's actually super diffuse. Yeah, it's like taking the mass of the sun and spreading it out over, a light year, right? Or like half of a light year, right? So imagine this giant cloud, and it's so diffuse that the atoms are moving really slowly. They occasionally collide into another one, so their kinetic energy is low. But the overall potential energy, you still have the total mass of the sun. So they're all kind of hanging together. They're all orbiting, in effect, this total mass of the sun, occasionally running into one another. Now, then note the fact that space is really, really cold. Outside of this ball of gas, outside it's like 3 degrees, like 2.7 degrees. It's like literally 2.7 degrees. So, right, this ball of gas is, yeah.
Oh, sorry. I was going to say, it seems like that would that lend itself towards like condensation reactions? Wouldn't these gases be like combining as they cool down? It just seems. I'm just thinking of what happens on Earth.
Yeah, you're talking about hydrogen and helium, right? So these are really simple things, right? So people do, talk a little bit about hydrogen forming ice, but let's forget about that for a second, right? It's just like little, very simple, atoms flying around, and this ball of gas, which is half a light year across and solar mass or something like that, will in time cool. Right? Because outside it's even colder than inside the ball of gas. What does it mean to cool? What does it mean? Like temperature is an average quantity, right? Temperature is just telling you how fast the molecules are moving. So in fact, what it means to cool is that the molecules are slowing down. As they slow down, they have no choice but to fall deeper into the potential well, right, into the gravitational pull of the star, and then that whole process goes unstable, and the whole thing collapses on itself. Right now, if this was a perfect ball, right, that just wasn't rotating, it was perfectly, still, it would just fall down and make a star, and that would be it. But in reality, that would be an oversimplification, right? All clouds are turbulent, and we can sort of see that by looking up at the clouds on Earth, right? Flying on an airplane, right? You know that clouds are kind of turbulent, right? So that sense of that turbulence gives every collapsing cloud that's about to make a star a sense of overall rotation, which is very small. But then, just like a ballerina that jumps up and brings in her arms to spin up, when you take this stuff and you collapse it down to the center, right, it spins up, right? And that's where that, process of making a disk comes from. It's a lot like, even though it's not exactly the same, but it's very much related to how people make a pizza, right? And you take a ball of dough, you throw it, and you spin it, and then it makes a pizza. At least that's what I've been told. I've never made a pizza myself.
Usually you just put it down on the table and you like spread it out,
Usually you just call a man, and he just like arrives with it.
There was a place in New York when we lived that was called Pizza Boy 2, and Pizza Boy was always at the ready with the pizza.
They had
Yeah,
us on I want to say they had us on speed dial, but they knew where we lived. We didn't even have to tell them who we were.
So my question is, where does the ball of gas come from in the first place? Is it a nova source? Is it accretion of some other form? What is the origin?
So the origin of all matter in the universe is the Big Bang, and it's a little bit weird. There's
I'm thinking like way downstream of that, not necessarily like where does the first atom come from. I'm thinking of where does this accretion of it's a nebula that we're talking about, right?
Well, it's no, we're talking about giant molecular clouds, right? So these are just like kind of the way you spot them with your telescope. You can need a very big telescope, but the way you spot them is as you scan across the night sky, occasionally you'll be like, wait, there's no stars there, right? What's going on? And the answer is that the stars are being obscured by a cloud. And the Milky Way is just studded with these giant molecular clouds. They range quite a bit in their mass. They go from kind of solar mass scale to on the large, and they can get up to really high masses, like 10,000 solar masses.
And so where do they come from?
But right, so this is just hydrogen and helium gas that forms, early in the universe. And then kind of gets recycled, of course, through the solar through the stellar lifetime. What you're talking about when you say where do the metals come from, those predominantly come from supernovae. So when the universe is born, it's born almost entirely out of hydrogen and helium. There's a little bit of lithium, but it's a very boring place actually, because there's just like not the kind of periodic table is just not filled in. In fact, it's boring, but it's in a universe I prefer because I don't like anything heavier than lithium. I just can't remember
It's
the
much
number
easier.
of protons. Yeah. But then as you form stars, right, stars go through their lifetime where they kind of eventually convert hydrogen into helium into more heavy things, and stars that are particularly massive then blow up as supernovae at the end of their lives and spew out the whole periodic table basically back into the universe to give it the next kind of generation of stars, next generation of disks that are going to be more enriched in everything heavier than hydrogen and helium.
So, but the molecular clouds that form that allow for this gravitational collapse, they're you would link them directly back to the origin point of the universe, or they come together over the course of the lifetime of the universe de novo?
Well, yeah, they come together over the lifetime of the universe, but the material that makes them is indeed the primordial, hydrogen and helium.
The primordial ooze. So how does the cloud of gas come together, right? So you have a
It makes me think
universe.
of clouds on Earth. I've been studying cloud formation on
Yeah.
Earth. We had a conversation with someone recently about this, and I realized I knew nothing about it. And yeah, it makes me think of all the fascinating nucleation events. And Dr. Basri from Berkeley, when he was on the show, he mentioned that dust particles played a role in this nuclear. Like there seem to be some parallels between cloud formation on Earth and this molecular cloud formation that seeds what will become a star. Yeah, I wonder if you had any thoughts on that.
Yeah, are they forming like planetary clouds? Are they special or
So there are some parallels, but they're certainly not one-to-one, because the clouds on Earth are not gravitating, right? They're not being held together by the gravity of the cloud, right? They're being held together really through other processes. And like,
Electrostatic, probably.
yeah, I mean, like clouds on Earth are actually extraordinarily complicated, right? Cloud formation is not well understood, I would say. In fact, like that's if I again, my background in this is relatively limited, but I think my understanding is that much of the error in like climate predictions, right? So like what's going to happen as the climate warms up, what's the number of degrees by which we heat up? Much of that is due to the uncertainty in how the cloud albedo feedback is going to work.
Man, it's so true. Like that's happening right now where we live. Like we're supposed to have 100-degree temperature day yesterday, and since we have forest fires right near us,
the smoke is thick enough that it's dropped it down to
it's like 20 degrees colder than it's supposed to be.
I think it's more than that. I think that it's 65 and it was supposed to be 100.
Yeah, it's crazy.
Yeah. That's right. You guys are battling climate change one forest fire at a time, right?
You know,
Like cooling
there
down.
is, yeah, it's nature's chemtrail.
Yeah.
We were actually out in
Yeah.
the woods. We were in the woods the other day, and we were like, "Yeah, this fire is kind of nice actually," because we'd be like burning in the sun otherwise. And we were swimming in this nice creek, and we were just like, we were trying to like
Nature's Chemtrails is like a good name for like a folk band, you know.
We were thinking
Like,
we'd start a YouTube channel where we just laud the benefits of chemtrails and maybe
Review forest
There you go.
fires.
Yeah. But to kind of get back to what we were talking about, in the astrophysical clouds that we're talking about, right? They are predominantly being held together by gravity because they're on a much larger scale. This is a gas that if you were to kind of spread it out evenly, but introduce just a little bit of noise on top of it, the parts that are slightly overdense will attract other parts, and they kind of grow through just a gravitational manner. Does that make sense?
It does. Is anybody playing with the idea that electrostatics could play a role in that, like they do in cloud formation, or what? Anybody looking into specifically the chemical side of that? I mean, it's interesting that the hydrogen exists in a molecular form, or even that they're called molecular forms instead of like ionized molecular clouds instead of ionized clouds or something.
Yeah, ionization and generally magnetic fields play a big role in their evolution. In fact, one of the kind of in the simplest story that you can tell is that the overall rotation of the clouds is set by the direction of the magnetic field, because the magnetic field pierces the cloud. Now, even if your ionization fraction is tiny, right? Now those ions are going to be, just because the magnetic Reynolds number gets kind of high, right? They then will kind of freeze in the overall sense of rotation to the symmetry axis of the magnetic field. So then when the collapse happens, you fall down the kind of symmetry axis of the magnetic field, and that's what sets the direction of where your disk is going to, how your disk is going to rotate. That's of course an oversimplification, because as I mentioned just a little small number of minutes ago, these are turbulent systems. So there's not really a single sense of like here's a ball, let's slowly rotate once per 10 million years this way, right? Its rotation is fractal. But even in that turbulence is in part driven by magnetohydrodynamic processes. So absolutely, magnetic fields play a very important role in the early formation of planetary systems.
What about the electrostatics of those molecules interacting with each other? Is anybody looking into that, or is that talked about at all?
Oh yeah, I mean, like I'm not a chemist, but people worry about all kinds of, all kinds of very detailed chemical modeling what's happening to NH3 plus, right? Like that's if or like, yeah, I think it's I'm not gonna lie, right? It's like NH3 plus is what came to mind, but I'm not sure that's actually right. It might be some other molecule. I hate molecules.
You hate molecules, just as a
I hate
baseline.
molecules. I only know about hydrogen, helium, and that's it. Okay, that's it.
Yeah. Well, that's what kind of what I'm getting at. I just wonder if there's this whole other layer of things that since people who study astronomy tend to have physics backgrounds, not chemistry backgrounds, I just wonder if there's a layer there that future generations will uncover one day.
The astrochemists would like a word.
The early astrochemistry.
Chemistry is a huge industry, right? It's only dumb people like me that only know about hydrogen, helium. There are smart people in the field that are well aware that there are things heavier than hydrogen, helium, and astrochemistry is generally becoming not only is it a huge industry, it's like getting to a point where it's not just trying to like reproduce a spectrum of some protoplanetary disk, right? It's getting to a really beautifully detailed, very quantitative state where they're making all kinds of progress. So yeah, people are very much thinking about that problem. I'm just not such a person because I can't remember any of the molecules. Like I don't even know what I'm breathing right now. Right? It's probably hydrogen.
It's just some stuff. It's fine. It's fine.
Yeah.
It's not that important. It works is what's important.
Exactly.
Now that we've covered the birth of stars, I want to ask you about the death of stars.
Mm-hmm.
So the conventional story, when you look at diagrams of stellar evolution, they end in novas. For the
sometimes.
Most of the time, no?
Let's look at the stellar evolution diagram on Wikipedia.
Yeah.
Just like a bunch of different routes they can take.
So while you're looking at that, I guess the question is, what are the ways in which stars die? And why is it that we see so few novas?
Well, so there's basically two routes that stars can go by, right? One, if they're somewhat more massive than the sun, right? Think, roughly factor of 1.5, then they can go supernova. And that process is very, very short. In fact, capturing that explosion is one of the coolest things you can do, because you mentioned chemistry. You get to see, right? You get to see the enrichment of the universe in kind of the previously less represented part of the periodic table, kind of in real life. But the supernovae are kind of short events. You see supernovae remnants all the time.
Short events on human timescales?
I think they only last a few tens of thousands of years, right?
So supernovae explosions themselves last really, they're like seconds, right? So you're really capturing, but then the remnants last for a long time, right? In fact, there was a supernova remnant. I forget exactly which one, but you could trace the explosion to something like the year 16 something or other, because there's drawings of it all over the world. Like in all cultures, like all cultures noted that there was a weird star that appeared that was visible during the day for a little while. But stars like the sun that will not undergo supernova explosion die a very boring death. right? They will first become giant. This will happen to our sun in 5 billion years, right? And that will, probably engulf the Earth, maybe not, but I'm really rooting for the sun. I think we've done, we've done so much damage that we would deserve it. Frankly, at the end of the day, if the sun was just like, all right, you guys are done, and just engulf the Earth, I think Mars might be saved. And then afterwards, right, the sun goes through this, process of mass loss, and like that's where the planetary nebula, the so-called planetary nebula is a confusing name, but it's a process during which a lot of the mass will get blown off. Then the sun will become a white dwarf. It'll just sit there slowly burning through the rest of like a little bit of its leftover nuclear fuel, but it'll be a very, very boring death. Eventually just go kind of dark. We're extrapolating into very deep future now.
And so when you extrapolate into the deep, so I have a constellation of things that lead to a longer timeline, which is that for a long time we used to think that the expanse of the universe was just the Milky Way. We learned to look beyond the Milky Way. We saw that the universe was much bigger. Now we have the James Webb. We're looking out to the edge of the universe, and we're like, whoa, hey, that's weird. We have fully formed galaxies 200 million years after the Big Bang. Now there's sort of, it seems up in the air as to whether or not the Big Bang is going to get pushed back or not. Like, let's say it does get pushed back, and the age of the universe is actually much older than we realize, because it's going to be another Milky Way to Hubble sort of jump with the James Webb. If the age of the universe is much longer than we realize, what happens after you go from white dwarf to black dwarf? Is there a different path of stellar evolution that over such long periods of time you can imagine where they might
will the solar systems collect the black dwarfs and make something out of them?
Or collect the black dwarfs? Could you have a star that dies in such a way where the rocky metallic core is maintained and it's not blown off and it gradually becomes a rocky planet? Are these things that are possible?
You're asking all the right questions. So first, I don't think that the age of the universe is going to get pushed back. I think the Planck data, which is a different mission from about a decade ago.
For the CMB.
I think that's been, the CMB, right? So like that's got the age of the universe, I think, pretty well nailed down. The fact that there's fully formed galaxies only 200 million years from the time zero is telling us something remarkable about structure formation and kind of how rapidly that can ensue. But I don't think that the age of the universe itself is going to change much from the 14 or whatever the exact number is, billions of years. But to answer your other question, as you go into the future and the white dwarf just kind of cools down to nothing, it's just going to be a iron core, with a largely helium atmosphere. It's going to be very boring. And then
look like a moon. Say,
what happened? I mean, it's going to just look, well, it's still half a solar mass, right? So it's not a tiny thing. It's sort of the radius of the Earth, but it's a very massive thing. And then you can ask the question, well, what happens after? What if you just keep extrapolating in time forward forever? Well, the universe is expanding, right? So the distance between things is growing. So if you really start to push this into the deep future, what you're going to be at is an even more boring universe where your kind of horizon, right, is going to be very limited. So that white dwarf that we talked about, the amount of the universe is going to get so big that the time scale for light to travel to, say, the next star is going to be not the time scale, but the expansion of the universe between neighboring stars is going to be faster than the speed of light. So your horizon shrinks and you kind of become isolated into your own little observable universe.
Maybe you can help me understand something about the expansion of the universe, which is that if the universe is expanding, wouldn't all of the objects within the universe also be expanding, therefore creating no net change? How is it that
Yeah, the thing that counteracts the expansion of the universe is gravity. So the expansion of the universe really you can think of as the fabric of space-time itself that's expanding. So the best analogy that I like is kind of like take a rubber band, right? Take a rubber band, or take better yet, a surface of a balloon, since we talked about balloons before, right? And imagine you're blowing up the balloon, right? Imagine you're a creature that lives on the surface of the balloon, right? Suddenly, it's like the space between points itself is expanding. Now, if you're a creature that is gravitationally attracted to another creature on the surface of a balloon, you can still kind of meet one another and hang out. And that's what kind of galaxies are, right? They're the gravitational counteraction of the expansion of the universe. But if you're here and there's a pair of other creatures here and the balloon is expanding, the distance between you is still growing. And eventually, if you put a speed limit on the rate at which you can transfer information, you can imagine reaching a state where the space between you is expanding faster than your signals can travel. And that's what the whole business with horizons is all about, right? It's that you kind of get isolated from being able to communicate, from exchange any information, including light, right, with other portions of the universe, because the balloon is big and it's growing ever bigger. And so you draw a line to a circle on this balloon around you, where like that becomes the horizon with which you can communicate.
And so so if it's the space that's expanding, what is doing the expanding? Right? So it's the objects are constrained gravitationally, they stick together,
Yeah.
they don't expand. But the distance between them is expanding. And so isn't that something from nothing? Doesn't that violate
Yeah.
isn't
And
that a
here
foundational
you have
violation?
and
Isn't
here you
that a magic
have
trick?
it's a magic trick, and the key to every magic trick, right, is to choose a really good Greek letter to reproduce it. Okay, like,
I'm gonna write
if
that
you're going to
down.
have a fudge factor, right, if your fudge factor is a lame letter like A, okay, like no one's going to believe your theory, right? It's just going to, like, B is also really bad. But lambda is excellent, especially capital lambda, excellent. So yeah, look, this is you've gotten to a really important point. And this is the fact that we really don't understand what's driving that expansion, right? The name that is given to that entity is dark energy, which is different from dark matter. They're unrelated things. But what is the fundamental nature of dark energy? Was vacuum energy? No one knows. But we see the expansion of the universe. This is not just like, people are not just making this up. Like, we actually see the fact that distant galaxies are redshifted away from us. So
Well, there is this interesting tension between that recession and the one that you mentioned with the Planck satellites, right? There is a tension where there's some discrepancy in that
yes,
actual, right? So that's
the
interesting too.
actual number is indeed, there's the Hubble tension. I'm not a cosmologist, so I don't follow this field very closely, but my recollection is that it's sort of in the 0.7 something, 0.72, or something or other. So yes, there is the bit of tension in the number itself, but it's important not to throw away kind of the entire thing, just because, I mean, that tension in the number might lead to some really deep insight into the physical reality of the origin of dark energy, and frankly, like, it would be awesome if it did, right? But the expansion of the universe itself, that determination is relatively straightforward. Like without knowing why it's happening, you can just tell that it's happening from the same principle as why the ambulance changes pitch as it goes by you, right? I mean, it's just a Doppler effect. So this really is happening. The universe is a confusing place.
I mean, it's interesting, right? Because you can't put it in a box and do an experiment to see if your interpretation is correct.
Yeah.
And
Well,
that's the thing that makes a lot of science so robust, is that you can put it in a box, right? If you have bees that you are like, well, why do they dance? And you can move around the flowers and you can show that they dance in a specific way to get to the flowers. And if you move the flowers, they don't get there. You're like, well, eureka.
mhm.
But with something like the expansion of the universe and the addition of dark matter, you can't put it in a box. And
That's true.
there's a lot of
The,
spiritual need almost to have an origin.
well, look, I mean, I would say that I would disagree here because there's a whole bunch of stuff we can't put into a box, right? You can't put a star into a box, right? You can't put a planet
Exactly.
into a box,
But we could be wrong
and it
about
doesn't.
stars.
I don't think we are. I think
I mean, we're probably not,
star.
but we can't
Yeah,
touch them, you know? I mean, we can, I guess there's like this Parker Solar Probe and stuff, but yeah, we can't like just go down there and poke at it. And
but
it
you
isn't
can
an
probe them
interesting,
other ways, right? You can probe stars by looking at their spectra, right? You can probe
that's like
stars by
there's like
looking
an
at,
indirect level to that, right? That we don't
yeah.
have to deal with if we're doing laboratory science, which is, you know,
And like I've never seen as much as like I've talked about how much I love hydrogen and helium. I've never seen hydrogen and helium atoms, right? But I've measured hydrogen spectra and helium spectra in the lab, right? You can see the consequences of that. So I think that the beauty of kind of the reductionist approach to physics is it allows you to make specific predictions that you can observe about things that are completely outside of our human reach.
Mm.
I mean, what you're talking about is there's a level of magnetism towards things that you can do it at sort of the tabletop scale, right? Which is why I love the double pendulum, right? Like I can play with the double pendulum and note, and that's a lot like putting the bees into a box or whatever. Ultimately, I think that's how all of our like actual understanding works. We in the end have to always reduce our understanding down to something we can uh, kind of imagine, and it's very difficult to imagine the fabric of space-time growing in 4 dimensions, but we can imagine a balloon, right? A balloon expanding, and then using the same kind of mathematical principles make predictions about what we're going to see about the redshift of galaxies, and then test if that's true or not.
yeah, it's true. There's this gap though in the scale that's just very very strange. Like on Earth, we can play with hydrogen and helium, and they'll have these line spectra. But for some reason, when we look at the sun, well, you know,
Mm-hmm.
obviously there's like this whole there's a rationale for this, but we look at the sun, we see this beautiful black body
Mm-hmm.
spectrum, and of course, like the atmosphere has different lines and so forth, but it's a very different matter than on Earth because there's no real way to take a bunch of hydrogen on Earth and get a black body spectrum out of it. And so you have to make this
Yeah.
leap, this theoretical leap to explain that you can't really go and try out because you can't build one, you know.
Well, yeah, and I think it's also important to keep in mind that all of science, the science is not really um, it's not really the procedure of going from we don't understand to now we do understand and the book is closed. It's this infinite number of steps that get you to a successively closer approximation to the truth. So the black body spectrum, right? The Earth's atmosphere is also a black body spectrum to a pretty good approximation. And if you're a spy satellite, for example, you then say, okay, we want to find where that approximation breaks down, where we can see through the atmosphere, right? You try to find bands where you can see down to the surface where water is not absorbing. So and the same thing with stars. Stars are black bodies. They're really good black bodies for the most part. But if you really want to inquire about the composition of the star, you look for lines that are not that kind of stand out from the black body spectrum.
Yeah, and those lines are really easy to study on Earth, but you can't make a black body out of gas on Earth, basically, which is really an interesting conundrum.
Um, Sure, you can. I mean, you can make a black body if you've got a balloon. I mean, the whole shtick with black body radiation is if you've got a bunch of oscillators, right, that are all in equilibrium in a box, in a black box, so you don't know anything about what's going on inside that box, and you measure the temperature, the spectrum of that box, you get the black body radiation. So you can get pretty close to a black body radiation. In fact, I don't know, I think that on that blackboard, if we measured its spectrum, it would look a lot like a black body.
Oh yeah, the blackboard would for sure, but I'm talking about like a gas,
Right, because when you're measuring the black body inside of a cavity, it's the cavity that is giving off the radiation, not necessarily the gas that's within it.
Yeah, so you have to measure the temperature of the balloon, so to speak.
And that's the thing, right?
The balloon has like a surface.
When you measure the surface, it's from what I understand, the continuous spectrum of a black. So we went down this rabbit hole a little while ago where we were looking at black body radiation and studying the sun, and there was I read Kirchhoff's original manuscript about spectral determinations, like where he first figured out about the law of emission. And he talks about a couple of things. He talks about the fact that a solid object will give off black body radiation, a continuous spectrum, that gases will give off line spectra, and a gas in between a solid object and your detector will absorb in lines. Right? And then
so far so good, yeah.
And then he basically he writes more about it, and he talks about it, and he's giving off his perspectives of why that is. And then if you go to the Wikipedia page for Kirchhoff's law, there's a third point that's been added, which is that a sufficiently large ball of gas gives off a black body spectrum. But if you start digging through the literature, you can't, it doesn't have a citation. You can't trace it down. It's taken as a given. But I cannot find the original source where somebody did that experiment and was like, here, look, it does.
There's a great story associated with, I think Kirchhoff was the person who did this experiment. So the story is that him and Bunsen, like of the Bunsen burner fame, right? They were hanging out all the time in Heidelberg, like they were friends. Just like lighting stuff on fire with the Bunsen. I'm assuming, right? I mean,
that's literally what they were doing, because he invented the spectrophotometer, and so Bunsen was like, wait, hold on, let's add this flame.
It's like, bro, like pointed this way, right? So they invented the spectrophotometer, and then one morning they saw down the river, like I think it was Kirchhoff who came out in the morning, like to have his coffee or smoke a cigarette or whatever, and he saw a bunch of smoke coming up, like from far away, from down the river, and pointed the spectrophotometer at it, like noted down what he saw, and it was all this like weird stuff, right? Like when you matched up the spectra, it was just like stuff that should not be in the atmosphere, right? Just like very heavy, like heavy metals, and like not Metallica heavy metals, but like like proper heavy metals, right? And he was just like, oh, like this doesn't work, right? Clearly, you can't do remote sensing. And then the next day, he read in the newspaper that there was a chemical factory that caught fire, and that's where the smoke was coming from. And it was then he was like, oh my God, it was actually given the right answer, right? The heavy metals that he was detecting really were in the atmosphere. And that's when he got the idea to point it at the sun. to try to get, the spectral lines of the sun. It's a beautiful story. Now, the question of at what point, right, do you go from kind of a gas that where you just like measure its lines to a gas that looks like a black body, I think has to do with achieving local thermodynamic equilibrium, right? But what you're asking is a good question. I would have to dig deeper through the literature to have a good quantitative answer for you.
If you could find that citation, I would be forever grateful, because from what I understand of black body radiation, the reason that solid objects that have lattice structures are able to give off black body radiation is because of electron delocalization. Like when you have a gas that vibrates, it vibrates in a specific mode, and that gives off...
Like a limited mode. There's like limited degrees of freedom with a gas, but...
And so you get a single line spectrum.
In a lattice, it's essentially an infinite spectrum of vibrational modes.
And so if you don't have the lattice, and if you don't have that kind of electron delocalization, how do you get the kind of continuous, smooth irradiance
like
that you get from the sun?
Explanation,
Which is the photons are bouncing around in the middle of the sun for millions of years, and they come out. And so,
That's right.
Perhaps. But I would love to see a reference for any approach to it experimentally. So if you could find that, I would love it. Because I was shocked, because I read Kirchhoff's book that he wrote after his experiments with Bunsen, and it's not in there. It is assumed to be a given, and it's not in there, and I would love to find out how it became to be a given.
Yeah, that's interesting.
I could be totally wrong, right? Like maybe I misread it, and this is just a question of having misunderstood it. But I looked, and I was really surprised, because you can get plasma can give you kind of a continuous radiation spectrum, but it has
like a
weird
bump under pressure.
Yeah, like it's Bremsstrahlung radiation,
spike.
And so it's got this really weird shape to it, so it doesn't look like the sun's black body. And so I was just I've been curious ever since then. And so any physicist that I get on the show that does anything with stars, I always ask, and no one's been able to offer the citation. So if you can help me find it, I would love that.
Okay, well, yeah, it's an issue. Who were the first? Yeah, who were the first people to understand this? You're saying it's
there was a
Kirchhoff's
huge
book.
debate. There's a really interesting historic retrospective I read about the sun. I can't remember the name of it right now. And there was just so much warring going on in the scientific community about what was causing, what was the structure of the sun? Like, was it this shell that contained a gas? What caused this opacity? There's a really heated there's this many years where it's just going back and forth, and then the Eddington thing happens, and people just move on. It's just like, all right, done. And
it was it Herschel who thought
like Herschel and
the
James,
Solarians,
and there's
but there was the
Italians
Solarians.
involved.
He thought Herschel was convinced that there was a race of people who lived on the sun called the Solarians underneath the ignited atmosphere of the sun, because they could see through the sunspots that it was dark down there. And so they're like, oh, we must be looking at a rocky planet, because if it wasn't a rocky planet, we'd be able to see the other side of the sun through it. And if it's a rocky planet, there's clearly a race of people called the Solarians that live down there.
Different
Maybe
times.
there are. I mean, no one's checked. Like you're saying, like no one's ever gone and checked. They're all probably making fun of us.
Well, have you ever read any Thomas Gold?
Thomas Gold?
Yeah,
Like
Thomas Gold.
the Cornell professor?
I think so, yeah. From like the 70s.
Oh, sure.
Yeah,
so, of course, yeah.
So he wrote The Deep Hot Biosphere. And in The Deep Hot Biosphere, he has basically a model for life that is not carbon-based and not of our scales. And I've always kept that with me. Like whenever I look at the sun, I always wonder.
Yeah. Tommy Gold was famous for being right a whole bunch of times without doing the calculation, right? I mean, he was that's
what I'm aspiring to. That's my benchmark.
Yeah, me too. Yeah, no, he was a really opinionated guy. His one of his students, Peter Goldreich, is still around. He's a professor emeritus at Caltech, and I've had the pleasure of having numerous discussions with him. And yeah, there are crazy stories from like the 60s with Tommy Gold. But my doctoral advisor, Dave Stevenson, was a TA for Tommy Gold at some point. And Dave used to tell me that there was this like Tommy Gold was just kind of, he would just talk about ideas. He'd be like, it's clearly should be obvious to you that da 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 da. Right. And that thing would be like completely not obvious to anybody, but it was really obvious to him. But also he could not do calculations. Right. He at one point during this class tried to write down a single equation and got it wrong. And the equation was E equals MC squared, and he got it wrong. He wrote E equals MC. So he had no capacity to.
That's awesome. I wonder if he did that on purpose, just to sort of,
to drive it home.
No, he did not. Right. He was an extraordinarily creative, astrophysicist with remarkable intuition and no capacity to do calculations, which kind of like begs the question more generally, like, is there more than one way to really do physics? Right. I mean, it is true, right, that people fall on different parts of the spectrum. Some people are very mathematical. They think kind of very algebraically. Other people are very geometrical. But you can't really do physics unless you have a very solid mathematical background, right? That's just not part of the career. And at the same time, one wonders where's that range? Where's that spectrum really end in being able to make useful contributions? We know that if you're very, very mathematical, you can definitely make useful contributions, but where does it end on the other side?
Well, you can always collaborate too, right? I mean, even Einstein was collaborating with a mathematician on his greatest works, and I found that to be the case. Like, I have sort of middling mathematical abilities myself, but I've always found a way to make myself useful conceptually in collaborations, where especially from a material science background, where I can think about things, like you said, maybe more like geometrically or in terms of their interactions physically, and then find people, reach out to people, collaborate with people that are specializing more in the, say, fluid dynamics or in the deformation mechanics and things like that are heavily mathematical. So
absolutely. I mean, me too. I'm okay. Like, I'm not but I'm by no means a very good mathematician. I've
seen a lot of pictures of you in front of blackboards covered in mathematical equations.
It's just like fake news. Don't believe everything you see on the internet. Right?
Fascinating.
It's just like I don't understand what any of that is. No, but in all seriousness though, like I get, I'm okay and I can sort of do what I need to do, but I do not have a mathematical, like, do not have mathematical imagination. I have kind of geometrical imagination. I can imagine how stuff happens very vividly, but it takes me a while to download that vision, if you will, into a quantitative model.
Yeah, so that's sort of like the power of working in big communities, I think, too, is if you can look at things in that material interaction way and then work with somebody, then you can make all the more powerful publication as a result of it.
I mean, I found this in biology a lot, where as you delve deeper and deeper and deeper into a specific question, you end up falling short on being able to look at the bigger picture. And that often, in my experience, correlated to people who were very technically proficient, but were not necessarily, I don't know if they didn't have the interest or the time or whatever else to step back and to look at the big picture. And sometimes paradigms have to shift, and I think that the people who are looking at the intricate details of one further step of the technological or the mathematical have a harder time generating the idea that causes the paradigm shift, because there's something about a depth of understanding where you can go one step further quite easily, but it's very hard to erase the entire blackboard and start over.
I understand what you mean, but I I firmly believe you can't have one without the other, right? Those paradigm shifts don't happen until your model gets so sophisticated that you can readily see where it doesn't work. I mean, think about like the example of the Ptolemaic, epicycles, right? Like the Middle Eastern scholars in the ninth, 10th century took that model like to some absurd level of complexity where the number of epicycles was astounding, and just like the calculations were getting really quite heavy. And it was actually the Middle Eastern scholars themselves that realized that this is not a convergent, program where you can keep on trying to fix the model by adding more and more episodes, but you will diverge away from the observations of the planets faster than you're able to correct from them. And so like it was that ability to drill down and get to the super technical, point that then gives you the license really to then fully erase the blackboard, right? So I think it's not. I fully agree with you that it's not. It's oftentimes not the same people that are doing the erasing and the writing of drilling, but I think you kind of the thing that motivates that rethinking, right? The thing that motivated general relativity, for example, right, was the fact that people started getting uncomfortable with the fact that there was no magnetic version of the gravitational field, and precession of Mercury's orbit was getting kind of problematic. So all of these things, but these were detailed calculations. Do you not agree? Like you don't. It wasn't just a spark of Einsteinian genius to say, well, no, let's reimagine all of gravity. It was motivated by the fact that it was not working with the existing detailed model of reality.
But for a long time there was resistance to that change though too, which is something that is I look out at the world now and I feel like science hasn't had a ton of paradigm shifts in the last 50 years or so.
Well, I think it's different sciences do go through their paradigm shifts and at different times. I mean, physics had this extraordinarily successful early 20th century where, in fact, the amount that was figured out was so large that I think we're still kind of grappling with interpreting what all the things that were figured out. So we're kind of in a way writing the success of the early 20th century.
And that interpretive level is exactly what those people who don't necessarily excel at mathematics are good to have on your team for, right? There's that interpretive level that's absolutely essential to science. And
like somebody's done the calculation and somebody else.
What the hell does this mean? It's like, oh, I think I know what this means, And there's so many of those at the quantum level too, where you just like, what does this mean? What is the significance? What's the material significance of this mathematics? And there's so much work to be done there.
Absolutely.
But you were saying that the paradigm shift, the fruitful exploration of the beginning of the 20th century it reflects different time periods of paradigm shift for different fields?
Yeah, I mean, I think that if you look at sort of the paradigm shift that occurred in this is a less important problem, if you will, but if you think about the stuff that I work on, right, planet formation theory absolutely right now is going through a paradigm shift of throwing away everything we thought we knew and rebuilding it from scratch. And the reason it's happening is because it's not because someone woke up one morning and thought, I really think the Earth formed in a different way. It's because we've started getting data for planets that orbit other stars, and we are beginning to see the like Swiss cheese of our planet formation theory is full of holes, full of things you cannot explain. And it's really that tension between the observations and the classical model that's driving a lot of that creativity. And you're right. There are those in the field who really want to hold on to the picture we had because it's a comfortable picture. We know how it works. We had worked out all kinds of things about it. And then there are people who say, "Oh, everything is wrong. We have to completely go back to the very basics." And the truth is, of course, somewhere in the middle. But that makes for a very exciting time in the science, in the
I
discipline.
feel like humans have always wanted to say, like, we basically understand how everything works. You know, ever since you read the writings of the ancients even, and they're like, this is how it works.
If you put a leaf of basil between two bricks and leave it in the sun, you get a scorpion, and the tree will produce birds.
It's like so certain about it, you know? And people are just like, yeah, I mean, it makes sense to me.
Yes, it's got to come from somewhere.
It like kind of defaults down to a bar conversation, right? Like, you know, when you're in a bar, like a long night, you're like, no, that's not that. Let me explain it to you, right? Like, and sort of, you know, that's where we always, you know.
That's kind of the goal of this podcast, actually. We try to get really smart people on the show and have a bar conversation with them, basically.
You
can go watch their lectures somewhere else, but we're trying
to. The night is young, yeah.
I mean,
it's true.
It's so promising to be at this point because I think that you're right that there is, after a period of stability, there is this moment where people have realized that it is possible to change the theories. And there is the tension between the people who suggested a long time ago that the theories should be changed but didn't have the math, and the people who have the math have started to catch up.
Or the observational validity.
The observational stuff too, but I think that it's a generational thing because you have a generation of scientists that come up in a certain way, and there's a few dissenting voices, and they operate maybe on the edges, and people pick up on their ideas because they think that they deserve to be developed, and then they develop them. And one of the things that we do is we really try to talk to the people who are like, no, we have to erase the entire blackboard, and see if we can pick out some pearls there, and then put them in front of the people that are doing the math, and putting them in front of the people who are changing the theories within the academy to see where those lines can be redrawn and where they can't.
I'm all about erasing the blackboard and never writing again. Just like we're done here. We'll never know.
It just
is. Where does the scorpion come from? What is a scorpion?
Who cares? Who cares?
As long as it doesn't come near me.
Yeah, exactly.
Man, there's so much to talk about. I feel like we've been talking for like an hour and a half. I know you're a busy dude, and you probably have
unfortunately
a lot of work to get
I've
back
got a really important thing to do, which is literally I have to get on a skateboard and go home and change my shirt for like that, you know. And I'm only half kidding.
Are you gonna put on a fancier shirt or a less fancy shirt?
No, just a Y shirt.
Okay,
you know,
just like a tuxedo.
That's the uniform.
Yeah, that's right. Exactly. Listen, you guys, it was a really a lot of fun discussing all of this with you. Hopefully, we'll continue this conversation at the bar, where we can really drill down on how things really operate and never question our beliefs again.
We will probably be in Southern California later in the year, so perhaps don't offer that too easily because we will show up at your door.
No, I will. I offer that in full seriousness, and it's like I never joke around about this. Sorry. Oh
I'd
yeah,
love to see your band sometime too. Yeah.
And the reverse is true. I listened to your stuff and really liked it.
Thanks, man.
Yeah.
So, guys, if you are listening to this, check out Seventh Season. Seventh Season is the name of the band. Is that it?
Yeah. You got it. Yeah, the Seventh Season band. Yeah.
And where else can folks find your work? Do you do any social media or anything like that? Or
yeah, I've been staying away from social media just in the last, I don't know, half a year or so, just because I've really had no cycles, no time to come up with like interesting things to say right, just because I have between starting a company and being a prof and recording music, right? But I will get back to posting on twitter.com at some point, right? I haven't been banned, right? I just haven't
Yet.
had the interest. Yeah, that's right. The
Maybe
night
just
is young.
hang out for a little while. Yeah, just let it cool
Just
down a
start
bit.
saying things, and I'm sure it'll come.
Yeah.
Cool, man. Well, it was a real pleasure.
Okay.
Thanks for coming by.
Yeah, it was really good.
All right. Thanks.
All right.
Okay.
Take care.
Bye.
See ya.